Welcome to Logic and Proofs. This is the first day's lecture. It'll be about 2 hours long, and I'll also post tomorrow's lecture, Tuesday's lecture. That will also be about 2 hours long. This is on YouTube, so of course you can pause it whenever you'd like. On Wednesday, we'll finally meet at Gear Library. That'll be at 12 o'clock noon, and it'll last until 2 p.m. Every weekday, and it'll last for a total of 3 weeks. So there used to be a course in Lincoln that used to be offered to 7th graders. Of course, back then they didn't have middle school math course 2. It was instead called pre-algebra. They had pre-algebra, they had pre-algebra diff, and then they also had this course called elements. And it was a 4-year long sequence that started in 7th grade, and the final year was in 10th grade. And it was a course that was offered through invitation, so like roughly 30 students were invited to take it, and then they would go together through that 4-year long sequence. It's no longer offered here in Lincoln, unfortunately. The teacher who used to teach it retired, and they haven't had anyone else teach it since then. So the first year of that elements sequence was an introduction to logic for about half of it, and the other half of it was kind of just pre-algebra notions that the other students were learning. And so this course Logic and Proofs, is going to cover all of the logic portion of that elements course. So also the second logic course I'm offering later in the summer, called Logic 2 Set Theory, that was the 8th grade portion of logic. So that was about half of the 8th grade elements course. So this course is going to be about pure logic. That means the stuff we learn in this course can be applied to anything where logic is required. We'll learn how to apply logic rigorously and correctly. Now, the second logic course I'm offering, called Set Theory, later in the summer, that's all about how we can use the logic that we develop in this course to start to define and develop mathematics as a discipline itself. So this course is more focused on logic in general, so it's super applicable to many other disciplines. And then the logic course that I'm teaching later is a sequel to this course, and it's all about developing set theory, which underpins all of modern mathematics. So this course content very naturally organizes itself into 3 different weeks. The key point in this course is learning how to develop logical demonstrations. So we're going to learn how to demonstrate a logical conclusion from a collection of hypotheses. So this first week is going to develop everything that we're going to need in order to start studying and making and looking at logical demonstrations. Now, I'm using the term logical demonstration as opposed to proof, because really a proof is when we're proving something mathematical using the rules of logic. Now here we're actually going to learn how to prove a logical formula from a set of hypotheses, and we'll talk all about what that means. So week 2, we'll start looking at some more complicated demonstrations. We'll develop some shortcuts that are called subroutines, and we'll look at 2 really important methods of reasoning. And I say here involving discharged hypotheses. We'll talk about later about what that means when it comes up. But the 2 really important methods of reasoning are proof by contradiction and using the deduction theorem. And we'll talk about those 2 things later. And then finally, in the 3rd week, we'll talk about universal and existential quantifiers. And those terms sound complicated, but really they're simple concepts. And of course, we'll talk about them when they come up. But that final week, we'll learn to apply what we learn about logical patterns and demonstrations to see how we can prove things in mathematics. And that will be the culmination of this course. So at this point, don't worry too much about those black words and terms over on the right side. We'll talk about and define them when they come up. But that's just to give you a quick overview of the 3 weeks. Week 1, we're going to work our way so that we can start talking about demonstrations. The second week, we'll do more complicated demonstrations, learn a few shortcuts, and talk about 2 methods of reasoning that are super important. And then week 3, we'll talk about universal and existential quantifiers. Those are actually super important when it comes to developing set theory, but we're just going to get an introduction to them in week 3. And then, yeah, we'll wrap up by learning how to use this logic to actually prove things in math. So yeah, these first 2 days, if you have any questions or comments or anything, feel free to reach out to me. I'll be available. But otherwise, on Wednesday, we will get together and we'll start talking about everything. Alright, so the course structure is there's going to be homework assigned at the end of every class, and there's going to be 2 types of homework every day. The first type is called for class. That kind of homework should be just completed that night and ready for class the next day. So you should just be ready to pull it out when we use it during class the next day. It'll just be graded for completion. And the second type is called two-hand in. And that homework assignment is you'll just do it and then you'll turn it in at the beginning of class the next day. And I'll grade it and then you'll get it the very next day. Now, I say grades because while this isn't really going to give you any credit for Lincoln Public Schools, I will grade this course for fun. So I'll give you the grading scale on Wednesday, a copy of that, and the point distribution for 4-class assignments and 2-hand-in assignments, and also quizzes. So we will also be doing a short quiz every day. Now, that's kind of hard to do on the first couple days because we're on YouTube, but starting on Wednesday, we will have quizzes. And they're not going to be too hard. They're just going to be a simpler version of what we've been doing on the homework. And of course, the grades are just for fun, just to kind of see how you're doing and have a way to reward you for the work that you do in the course. Now, since this content is quite different than content you see in class, the grading is going to be pretty lenient. I will grade everything. If it's correct, you'll get points, and if it's not, you won't. Unless, of course, it's the 4-class assignment, where if you do it, then you'll get points. If you don't, then you get 0. But for the 2-hand-in assignments and the quizzes, you will be graded based off of how much you get correct. But I say that I'm grading leniently because in the Elements courses, when they were in Lincoln, actually getting a 78 in the course was an A. That was the bottom percentage to get an A. So if you got anywhere from 78% to 100%, then you got an A in the class. And a B was like 60-something to 77, and so on. So it was pretty lenient. And I'm going to be using a grading scale similar to what Elements was graded like, just because the content is a little bit different and can be kind of hard. So ultimately, if you get 78% of all of the points in this course, then I'll give you an A. And if you get from a 66 to a 77, you'll get a B. If you get a 54 to a 65%, I'll give you a C. If you get from 42 to 53%, I'll give you a D. And then if you get 41 or below, then you'll get an F. But of course, this is all just for fun, and I'll print out all of this information so that you can always look at it on Wednesday. And also, just so you're aware, we won't allow any retakes on the quizzes, and no retakes on the homework either. So however many points you get is what you're going to get. So I'll of course correct the homework and the quizzes and give it back to you the next day so that you'll have the correct answers. And of course you can always ask questions, but since the grading is a little bit more lenient, there won't be any opportunities for retakes or extra credit. Now, I'll talk about materials that you'll need for this course on the next slide. There's nothing really you need to go and buy, just a couple things. If you can find around the house and bring them to class, then it could help you and be useful for you. I'm just letting you know that some of the slides for today are going to be kind of wordy, and it might seem like I'm introducing all of these complicated terms that you've never heard before, that you'll need to know, but really, you don't need to really remember everything I'll talk about today. I'll let you know what things you'll need to remember. And really, once we get to the actual logic, which we'll talk about soon, very soon, you will see that actually it's very, very doable. Another thing, when we meet at the library starting on Wednesday, if you want to bring any food or drinks, that's totally fine with me. It can be kind of a long class. And also, if you're in the algebra class from 2:30 to 4:30, you also might want a snack for the little half an hour gap there. If you are in the algebra class as well, you can use the time from 2 o'clock to 2:30 to ask any questions if you want. You can work on the homework. You can do something totally unrelated to the classes. It's really up to you. It's just a half hour to kind of transition into the next course. Feel free to bring your backpack, basically whatever you'd like. Um, so here I'm going to talk about the materials that you may want to bring to class, and or just have handy so that you can make the time in this course the highest quality that you can possibly make it. Oh, actually, I forgot. I actually do have the grading slide on here. Yeah, so if you want to take a look, the grading scale is down there below. Um, Obviously, if your total percentage is in that range, then you will get that grade. Notice that there's no B plus or C minus, things like that, just A, B, C, D, or F. And whatever your final percentage is, obviously I'm going to round it to the nearest whole number. So if you get like 77.6%, I will bump it up to a 78, for example. Now, the 4 class assignments, those are going to be 20 points each. So starting today, you'll get a 4 class assignment up through Thursday of the final third week. So that's 14 days of 4 class assignments. They're 20 points each. And then also the 2 hand-in assignments, those are going to be longer. So those will be 100 points each, and you'll get one today, every day through Thursday of the third week. So obviously Friday of the final week, you won't get any homework because there's no class after that to get it back or anything. So there will be 14 of each of the 4 class assignment, 14 2 hand-in assignments, and there will also be 14 quizzes. Since I can't give you a quiz tomorrow, I'll probably give you 2 quizzes on Wednesday, but they don't take very long, so don't worry about that. And I'll tell you what'll be on the quizzes, of course, so that you know what is expected of you on the quiz. And then, since this course does cover 2 weekends, this weekend, so like on Friday, I'll assign you 90 extra points of homework. So that'll happen twice. So both weekends, I'll give you 190 points on your 2 hand-in assignments. So that'll be worth 190 instead of just the normal 100 points. And in total, that gets us to 2,000 points. So it should be fairly easy to figure out what your total grade is, because when you get your assignments and quizzes back, it'll have the grade on it, so you can add it up and see how close you are to getting whatever grade that you want. So yeah. Also, I won't accept late assignments for credit. So if you forgot to do your homework or something, you will receive a 0. However, if you turn it in the next day or something, then I will grade it for you so you can have the answers, but you won't receive credit for that assignment. Also, just to let you know, if you miss a day, that's fine. we can meet either before or after the next class that you're here so I can catch you up. And of course, it won't cost anything extra to do that for a reasonable amount of occurrences. I'm pretty flexible, so if you have to miss a day or two, that's fine. Just try to be here as much as possible. And let me know if I can do anything to help you. So last summer, I had two sections of this logic course. Though one section had 5 students and another section had 3 students. The section that had 5 students, I'll tell you what grades they ended up with, just to kind of show you just kind of how they did last summer. So student A had a 98% when they completed the course, which is really good. Student B had a 94%. So both of those students got A's. Student C got a 71.7%, so that student received a B. And student D, they had a 90.3% at the end of the course, and that's an A. And student E actually also had exactly a 90.3%. They got different scores on different assignments, they just happened to get the same grade. So we got a 98, a 94, a 71, a 90, and another 90. I would say that this class isn't too hard or too bad if you pay attention and do all the work and stuff like that. The other section of 3 students, they not all of them did all their homework, so they didn't end up with too great of grades. But that's just what happens when you don't do all the things. So yeah, and I see that this says that extra credit opportunities may pop up. I don't think I'll offer any extra credit opportunities. However, if some circumstances like happen where maybe that'd be a good idea to offer it, then I will. But I don't think for now that I will have any extra credit opportunities for you. But so try to get as many points as you can. If you do the homework and you show up to class every day, you're likely to do really well. So don't worry too much about it. And one last thing about grades, the format of some of your answers may count for points. So it'll be really, really clear when certain problems will have to be formatted correctly. For example, in today's homework, I'll have you draw a truth table, and as long as you do that correctly, you'll get the points for that in addition to having the correct answers. But it'll always be super clear when that's happening. Okay, materials. Bring these materials starting Wednesday. I know it says tomorrow, but these slides are from last year, and there was only one day of a video last year, but this year there's 2. So starting Wednesday, bring these materials. Bring something to write with, of course. Maybe bring 2 or 3 in case it runs out of ink, or you can bring a pen or a pencil, whatever. Bring a notebook. So if you have a notebook lying around your house, you can bring that to take notes with. You definitely want to take notes at certain points in this class, and I'll tell you when it'll be a good idea to take notes, of course. You'll also want to bring a folder because there will be a lot of handouts in this class. You'll want to hold on to the homeworks that I'll print out for you, the quizzes, and any other additional handouts that I might give you. You'll definitely want to have a folder for that. And also, another reason to have a folder is the 2 hand-in homeworks and the 4-class homework sometimes you'll have to have loose leaf paper for that, and you'll want to put the loose leaf paper in your folder so that you'll be able to keep it and refer to them in the future. So yeah, it also would be a great idea to bring some loose leaf paper. Of course, you could always rip some papers out of your notebook to use as well for the homework, but you will have to have some paper to do the homework on. So some loose leaf paper might come in handy. All right, so let's get started with learning the logic. So there is a term that describes precisely what we're going to study in this course. Now, this course is about logic, but really it's called propositional calculus. Now, you can write this down if you like. However, you're not going to be expected to remember the term propositional calculus. You won't have to remember exactly what it means. This is just to kind of give you an idea of what it is that we're studying. So you don't have to write this down necessarily, but it might be interesting or nice to write it down just so you have it. So this is straight from Wikipedia, but it's a great definition. So propositional calculus, it's the branch of symbolic logic that deals with propositions and the relations between them without examination of their content. So I'll let you know what a proposition is. On the next slide or two, we'll define what a proposition is. We're going to be talking about mathematical propositions in this course. So we're going to deal with mathematical propositions and the relations between them without examination of their content. Now, what does that mean? In other words, we're not going to bother with the question of whether or not we're using the correct set of assumptions in our logical demonstrations. So we're gonna demonstrate a logical conclusion from a collection of hypotheses. Now, a hypothesis is something that you're going to start with, right? Hypotheses are things that we start with. They're assumptions, and we're going to see what they lead to. So we're going to study whether certain propositions follow from other propositions, right? So we're not going to study exactly whether a certain proposition is true or false. We're only going to study if that proposition follows from other propositions. And that's really at the heart of logic. That's at the heart of propositional calculus. Now, you may have heard the term calculus before. There is a course in calculus that people take in high school or college. This is kind of a more broad usage of the word calculus that just means like just dealing with and seeing the relationships between propositions. So it's not really referring to the class that can be kind of hard for a lot of students. It's not anything daunting like that. Propositional calculus is the study of how propositions relate to one another. And notice that in the definition of propositional calculus, it says that it's a branch of symbolic logic. So almost all of what we're going to do in this course, there's going to be a lot of symbols. And these symbols a lot of them are going to represent propositions, and some of the other symbols are going to represent relationships between the propositions. So this is symbolic logic that we're going to study. We're going to use symbols to represent things. So it's always important in this course, whenever you see a symbol, to understand exactly what that symbol is supposed to represent. What does that symbol actually mean, and what is it used for? And of course, every single symbol that we're going to use in this course, we will clearly state what is it and what does it mean exactly. Now, there's a lot of words on this slide in particular. I just want to let you know that you don't have to worry about remembering everything on this slide. Just remember the gist of it, at least. Okay, so the words proposition and calculus, we're going to define them. Calculus, obviously, that's an area of mathematics dealing with instantaneous rates of change. And if you're into mathematics, you will almost certainly take it in high school at some point. The word proposition has several meanings as well. In math textbooks and professional papers, a proposition refers to a true statement that's about to be proved. So in this class, proposition is going to mean a statement that expresses a concept that can be true or false. And calculus is not going to refer to the course that people take in high school, but it's in this course, calculus is going to mean a particular method or system of calculation or reasoning. And that's actually what I think is the key word, reasoning. So we're going to reason about propositions, okay? We're going to start with some assumptions. We're going to assume certain propositions are true, and we're going to see what we can deduce. We're going to see what we can conclude from those initial set of assumptions. So notice in the definition of proposition, it's just simply a statement. It's just a statement that's either true or false. Now, in this course, and this is really important, if you're going to write something down, I would definitely write this down. In this course, we're only going to deal with the kinds of statements, or another way to put it is we're only going to deal with the kinds of sentences that are propositions. So we're only going to deal with statements or sentences in the English language that are either true or false. And that means that exactly one of these two options is true for a particular proposition. So a proposition is just something that is either true or false. It's not both true and false, and it's not going to be neither true or false. Those are not options. And it's okay to say that a proposition is true or false, but we just don't know whether it's true or false yet. That's fine. A proposition is just something that is either true or false. We may know its truth value, we may know if it's true, we may know it's false, or we may not know whether it's true or false, but as long as it is either true or false, then it's a proposition. So, yeah, we just need to make sure that every statement that we're dealing with has an actual truth value. And that's not something that you'll have to worry about too much, because everything that we'll give you in the course is going to be a proposition that's either true or false. Now, you may be wondering, isn't everything either true or false? Well, there are some sentences that you can write in the English language that are paradoxical. I'm sure you've heard of some of these before, but you can't really say that they're true or false, right? They don't have a truth value because the sentences are kind of nonsense. We're not going to consider that, right? So just know that whenever we say that a symbol is going to represent some proposition, then that proposition is just going to be a sentence or a statement that's either true or false. And that's the main idea. Now, there are some sentences that you can write down in the English language that if you read the sentence, it's not clear really whether it's true or false. I mean, it might be neither, because the sentence is so paradoxical that it just doesn't make sense. And so the key point in this course is that we want to deal with sentences or statements that make sense, right? They're either true or false. And so this slide, obviously there's lots of words on this slide, but really the main idea of this slide is just saying that in this course, when you're talking about logic, right from the get-go, we're only going to talk about statements that make sense. They're either true or false, right? Because based off the rules of logic, if we start with a collection of hypotheses that we assume are true, we're going to deduce things that are true. We might be able to deduce that some things are false, right? If certain things are true, then as a conclusion, we might be able to deduce that, oh, this particular statement is true, but this one over here is false, right? But logic doesn't have anything to say about nonsense sentences. So That's the main idea. Okay, so in this course, truth and falsity will be denoted by T and F. So whenever you want to write down that a certain proposition is true, you're just going to write a capital T. And whenever you want to say that a certain proposition is false, you'll write a capital F. Now, just make sure to not do a lowercase t or a lowercase f. I mean, if you do, it's fine, I guess, but just for consistency, try to make all of your truth values that are true, just write a capital T and write a capital F. So a truth value is an assignment to a proposition of either being true or false. Now, remember on the last slide, we were saying how propositions are sentences or statements that are either true or false, right? They have a truth value, is basically what we were saying. Propositions, they have a truth value, and that truth value is either true or false. And sometimes we know what the truth value is of a proposition, and sometimes we don't know what the truth value is of a proposition. Sometimes we're trying to demonstrate that a certain proposition has to be true or false based off of logic, right? So an example of a sentence that we can make that is not a proposition, right? Because every proposition has a truth value, okay, if we come up with something that doesn't have a truth value because it's paradoxical, then it wasn't a proposition in the first place, right? It's not something we can use in logic. And an example, a great example, is this sentence is false. So suppose that the truth value of that is true. So suppose that the italicized sentence on this slide, suppose it's true. Well, if it's true, the very sentence it's saying that itself is false. And it's a contradiction for something to be both true and false at the same time. That's just not possible. So obviously that can't be true. That sentence can't be true, because if it is true, then, well, it's saying that itself is false. So it can't be both true and false. Not possible. So, well, then maybe the sentence is false. So if the sentence is false, then because the sentence says that itself is false, then it must be true. But we just assumed that the whole sentence was false. And if the sentence is false, then the sentence is going to say the opposite of what it says, and that means it's true, but then it can't be both true and false. Like, that's just ridiculous. So that statement is just not, we're not going to deal with those kinds of statements in this course because it doesn't have a truth value. So it's quite a different scenario than just that we don't know whether it's true or false, right? So that's super important. It's not that we don't know whether it's true or false. It's simply, it's not one or the other. It's both, right? It's not that we haven't figured out whether it's true or false, because we already showed that if we assume that it's true, then it also has to be false at the same time. And if we assume it's false, then it also has to be true at the same time. So it's not that we haven't yet determined its truth value, or we just don't know. It simply doesn't have a truth value. And so, just as a conclusion, we can't do propositional calculus with these kinds of statements because they're not propositions. So if I say that the capital of Texas is Houston, that's a fine proposition, right? That is an okay statement to have and deal with in our logic, because it has a truth value of false, right? The capital of Texas is not Houston. So if we're dealing with the sentence, the capital of Texas is Houston, it is a proposition and it happens to be false. Alright, so in this class we're going to deal with propositions. They have truth values. So, in other words, we're going to deal with statements that have definite truth values. And it doesn't matter whether we know what those truth values are, as long as we know that they're propositions, as long as we know that they have truth values, then we can deal with them logically. Okay, so the proposition that we dealt with earlier, Houston is the capital of Texas. That's a fine proposition. It is a proposition, and it has a truth value, and that truth value is false. If we consider the statement, this sentence is false, that doesn't have a truth value. It's not a proposition. And if we consider the statement, Boise is the capital of Idaho, that would be a proposition, and its truth value is true. Any statement or sentence that has a truth value is a proposition, and propositions always have truth values. Okay, so we talked about earlier, I introduced the term of demonstration, a logical demonstration. And at this point, it's okay to think of proof and demonstration as more or less the same thing. They technically have somewhat different meanings, but they're pretty close. So it's all right to think of proof and demonstration as interchangeable terms. So the purpose of a proof is always to convince people, and that person can be yourself. You want to convince someone of a claim. You want to convince someone maybe of a proposition. You want to convince someone that a certain proposition is true or that a certain proposition is false. Now, proving things is an essential part of mathematics. So, in math, every single result or concept or fact in math has a proof. And that's quite an astonishing thing. Yes, everything in math actually has a rigorous and complete logical proof. Now, the unfortunate thing is that schools really don't teach about proof much at all. Now, the first time you might see the word proof used in a math course is in geometry. When you take geometry, whenever you take it, you find yourself proving things, kind of proving. You do these 2-column proofs with facts about geometry, and that's kind of what proof is. It's not entirely rigorous proofs. I mean, they're okay proofs. They're pretty good, but everything actually, including geometry. But I mean, you only do proofs in geometry, which is unfortunate in high school, but even things in algebra have proofs. It's just that when you take algebra in school, they don't tell you the proofs. They don't show you the proofs. And actually, the very first time that you start to really prove everything that you see is in college. So it's actually after you take calculus, after you take differential equations, linear algebra, courses like that, then every single math course after that is all about proof. Now, obviously, you're learning new content and you're learning about new math, but you prove every single thing that you encounter. And actually, all of your homework are proofs. So, the purpose of a proof is to convince people, perhaps yourself, of a claim. Proving things is an essential part of mathematics. A lot of times it's just kind of skipped over. Sometimes you hear the word justification, and that's kind of like a proof, except it might have some missing parts if we looked at it closely. So justifying or explaining things is not the same as proof. Proof is a more demanding. So a proof is to convince people beyond any doubt of a claim, right? So this is what a proof consists of. we start with a set of known facts. So we always start with what we already know. Okay, things that everyone agrees are true, or, I mean, these things can be things we've proved before. They can be things that we already know are true, right? So if we're trying to prove something new, we're going to prove a new statement. We're going to start with a collection of things that we have at our disposal to use in our proof, okay? And then the whole process of a proof is we're starting with that collection of facts that are already known, everyone already knows it, and we're going to pave a logical pathway to that result. Now, this pathway must be unmistakably correct at each step. So each step of a proof needs to be unmistakably correct. Now, logic is the tool we use not only to construct proof, but also to verify it. When we're constructing a proof, we're doing logic. We're using logic. Now, every single mathematical result, definition, theorem, proof, and discovery. Now, logic has everything to do with that. It's very difficult to overstate how important the material of this course is, the logic part of this, because logic is what you can use to travel from what you know to what you want to prove, right? Anything that you want to prove, you start with what you know and you use logic to pave that pathway to the desired result. And we're going to use demonstrations to do that, right? We're going to start with what we know, and then we'll somehow use logic to get to what we want to prove is true. Okay, so now we're going to talk about a vocab word, simple sentence. Now, this is just the simplest possible proposition you can consider. Now, this just means a proposition that doesn't have any connecting words. Now, we'll talk about exactly what connecting words are, but connecting words are words like and, or, if, and then. So, some examples of simple sentences. We have fire is hot. Now, that's a simple sentence. Okay, fire is hot. That's a proposition because it has a truth value. Obviously, fire is hot, so this proposition is true. Now, I suppose you could debate with someone who is kind of stubborn and they might want to say fire is not hot for some reason, and they might try to argue with you. But the thing about mathematics is in mathematics, all of the statements are really pretty clear. Like it's either true or false. Like you can't argue. There's really no argument there. And I'm just introducing some sentences like fire is hot or elephants only live in Europe, things that are non-mathematical because they can be good examples of propositions, basically. Now, the sentence, the integer x is prime, right? That is a proposition that has a truth value based on what x is. Like, obviously, x is some integer. Well, which integer? Well, if x happens to be 7, then yeah, the integer x is prime. It's true. Now, if the integer happens to be 0 or -6, those are integers that are not prime, right? So the integer x is prime. That is a proposition that has a truth value of true or false depending on what x is in the situation. Now, elephants only live in Europe. That's a proposition. It's false. You are tardy for class. That's a proposition. That's true or false depending on the context. And obviously, if you're going to use that sentence, you are tardy for class, it should be like it is a proposition if it's clear whether it's true or false in that instance. But if it doesn't make sense, in some context, then you're just not going to use it, right? You can also say the boiling point of water is 50 degrees Fahrenheit. That's a proposition. It's false. And these are all simple sentences, right? So the sentence, this sentence is false, that's not a simple sentence because it's not even a proposition, right? So a simple sentence we're going to say is just the simplest possible propositions we can consider. And by simple, we mean there's no connectives, right? So notice how none of the above examples are negative sentences. Like, there's not something like fire is not hot or elephants don't live in Europe, right? There's no negation happening. If there was some sort of negation happening, then it would no longer be a simple sentence, right? And there's not a sentence here that says fire is hot and bright. That would not be a simple sentence. The sentence fire is hot and bright, that could be true, and it's still a proposition, but it's not a simple sentence, right? So we're just defining here a simple sentence, and we'll define compound sentences on the next slide. So in the English language, these connecting words like or and are used to combine two or more simple sentences. So those words, those connecting words, or and, we're going to assign logical symbols to them that are called connectives. And we're going to use connectives to talk about how two sentences are logically related. So to summarize again, a simple sentence is just a proposition. So it has a truth value, it's either true or false, and it doesn't have any connectives in it. It's not a negative sentence. It's not saying, like, it's not, for example, fire is not hot. It doesn't have a not in it, and it doesn't have or and it's not a sentence like, if it's raining, then I'll bring my umbrella. That's an example of an if-then sentence, and that's not a simple sentence. That's what we call a compound sentence. So at this point, just in your mind, make that distinction between simple sentences and compound sentences. They're both propositions, but they're going to look different symbolically, right? When we really get into the symbols in a few minutes, then you'll see that distinction. So a compound sentence could be a simple sentence that has a not on it, or it could be multiple simple sentences joined together into one larger sentence by connectives. So here's some examples of compound sentences below. The cat is alive, and the cat is not at the pound. If I get an A in this class, then I will be happy. Elephants are not mammals, or I am not asleep. If x is not the sum of two primes, then x is odd or x is not greater than 2. Okay, so the reason why we're making this distinction between simple sentences and compound sentences is because we're going to use capital letters. We could also call them propositional variables. We're going to use these to represent simple sentences. So, for example, in the first compound sentence up there, we could let the variable capital P represent the simple sentence, the cat is alive. In that same example, we could use Q to represent the cat is at the pound. And we wouldn't let Q be the cat is not at the pound because we want simple sentences to be letters. So we're going to introduce the symbols for the connectives on the next slide. But for right now, just know that that first example there, The simple sentences in that example are the cat is alive, and the other simple sentence is the cat is at the pound. So we could use P to represent the cat is alive, and we could use Q to represent the cat is at the pound. And then we would use connectives in order to symbolically represent the compound sentence, the cat is alive and the cat is not at the pound. And then likewise, for the second example, if I get an A in this class, then I will be happy. You could let P be I get an A in this class, and you could let the variable Q be I will be happy. And then symbolically, we're going to use a little arrow to represent if-then scenarios. So if P is I get an A in this class, and Q is I will be happy, the compound sentence, if I get an A in this class, then I will be happy, is just going to be P implies Q. And we'll talk about that connective later, but it's just going to be P and then an arrow and then Q. So really what we're going to do is we're going to let all the simple sentences be represented by letters, and we're going to use connectives or logical connectives in order to represent, in order to construct compound sentences. So compound sentences are going to be made up of simple sentences. So a compound sentence, if we were to write it symbolically, it might have one or more letters that have lots of connectives that connect those simple sentences. So a really big idea that I want you to keep in your mind right now is that any simple or compound sentence that you can think of, you can always create some sort of logical symbol for that simple or compound sentence. If it's a simple sentence, you're just going to have a single letter. It's just going to be one letter to represent that simple sentence. Now, it doesn't matter what letter you choose to represent that simple sentence, but generally, whenever we're in a situation in this class, for the sake of examples, I'll just start with P, and then I'll go to Q, and then I'll go to R, and then S, and then T, and I'll just start with P, basically, and then go down the alphabet whenever I need another letter. So simple sentences, their logical representation is just going to be a single capital letter, and I'll generally use P, and if P has already been used up in that same context, then I'll use Q, or I might use R, especially if there's several simple sentences being considered at once. Then we can use P, Q, R, and S all at the same time to represent those different sentences. Now for compound sentences, for example, that first example, the cat is alive and the cat is not at the pound, if we had a sentence like that, then we would be using a P and also a Q, right? The P would be used for the cat is alive, and the Q would be used for the cat is at the pound. And for the entire sentence, the cat is alive and the cat is not at the pound, that's going to involve a P, a Q, and then some more logical connectives that need to be added in to make that entire sentence. Now, if you just write down a variable, like P, for instance, you can use it to represent any simple sentence you want, right? So any particular formula, let's say, could have many possible sentences that are in its place. Okay, so here is where you should definitely start to take notes if you haven't already. This slide, we're going to introduce the first three connectives. So the first three connectives are right there below. But first, let's define the propositional variables P and Q to be the following. Let's let P be the simple sentence, I am hungry. And let's let Q be the simple sentence, I will eat a cookie. Now, for the rest of this class, that little caret symbol, like the capital A without that horizontal piece, that symbol will always mean and. Okay, so if you see P and then you see that symbol and then you see Q, that's going to mean I am hungry and I will eat a cookie. Okay, so if we let P be I am hungry and if we let Q be I will eat a cookie, then as long as we defined P and Q to mean those particular simple sentences, then whenever we write down P, that symbol, and then Q, we're going to read that as P and Q, and it's going to mean I am hungry and I will eat a cookie. The next symbol is going to mean or. This is the and symbol, but just upside down. It looks like a V. So if P and Q are going to represent the same simple sentences as the above example, then P or Q is just going to mean I am hungry or I will eat a cookie. Okay? And then the final, well, not the final, but the last logical connective that we'll talk about today, the tilde, that's often called a tilde, the little squiggle, it means not. So if we put a little squiggle in front of a letter, it means we're going to negate it. So since in this example we defined P to be I am hungry, if we have the little tilde P, it's going to represent I am not hungry. So this is super important. A formula is just going to be an expression that involves propositional variables like P, Q, R, S. It's going to involve those letters, those capital letters, and it's going to also involve connectives. So, for example, we can write a formula for the following sentence. It's not true that either I'm not hungry or I'll eat a cookie. Now, it's kind of a complicated compound sentence, but it's a really good example to exhibit the usage of these different connectives. So here, P is going to be the same thing as above. I am hungry. That's a simple sentence. And remember, we always let letters of the alphabet represent simple sentences. Now, Q, we're going to represent, it's going to represent the sentence, I will eat a cookie. So for that sentence there, that compound sentence, it's not true that either I'm not hungry or I'll eat a cookie. As you can see, there's a not symbol and then there's a bracket. That's because if you have the sentence saying it's not true that ... that part of the sentence, it's not true that's referring to everything that comes after the word that in this example here. So whenever you see something that says like it's not true that ... that's basically the same thing as negating anything that comes after that. So we have a not symbol and then we have brackets. And inside those brackets, we have not P or Q. That's because when P represents I am hungry, not P represents I'm not hungry. So it's not the case that either I'm not hungry or there's the symbol or I'll eat a cookie. So that is the formula for that sentence. It's not true that I'm either not hungry or I'll eat a cookie. So there's a formula. It's a perfectly good formula. A formula is just an expression that has variables in it and it has connectives. And one little thing is that those connectives have to be properly placed. For example, if you just wrote something like P tilde Q, like P not Q or something, that doesn't make sense at all because the not symbol, it just goes in front of a single letter. It's not supposed to go in between letters, right? The not symbol is supposed to negate a simple sentence. So whenever you have a not symbol, it's supposed to go in front of a letter, or as in the case of that formula below, the not symbol, it's negating that entire formula within the brackets, basically, like the sub formula or whatever. And that's fine. That's perfectly fine. But as long as the symbols are used correctly, then a formula is just an expression that has letters in it and it has symbols that are also used correctly. So let's see some more examples of formulas. Here we have 5 additional examples of formulas. Now, these are all correct usages of the connectives there. So these are actually proper formulas. Now, here's an important vocabulary word for you. A well-formed formula is just a formula that makes sense. It's just a formula that where all the logical connectives are used correctly, and just something that's a perfectly good formula that makes perfect sense. So as you can see, the not symbol, it's always in front of a letter or in front of a formula that's just supposed to negate that, right? And then the and the or symbols, they always go between, either between letters or between other formulas, right? Because they mean and or, and whenever you use the words and or in English, there's always some sort of phrase or item or other sentence that's on either side of the and or symbol. So yeah, a well-formed formula is just a perfectly good formula. So obviously those 5 formulas up there, we haven't said yet what P, Q, R, or S, what simple sentences they're supposed to represent. But really, I mean, most of the time, we don't care what the propositional variables represent. So this could be a potentially confusing point, but I just want to mention that in this course, most of the time, we won't care at all what the variables, like the capital letters, we won't care what those variables represent, but only whether they are true or false. So most of the time, when we see a formula, it's kind of like a variable in algebra, right? Like you use the letter x sometimes you don't really know what x is supposed to represent. Sometimes you're able to solve for x and you can figure out what it represents, but other times it's a variable, so you could put any value in for x because it's part of a function. And that's the way you should think of formulas in this course most of the time, right? Like that top formula, P and not Q, and not bracket R or S, that's a perfectly good formula, but most of the time we don't really care whether, what P, Q, R, and S represent. But the most important thing is that we know the truth value of P, Q, R, and S. So in this course, we won't be investigating how the truth values of simple sentences are determined or debate whether they're true or false, right? So we're not going to spend our time debating on whether a certain letter is true or false. We're only concerned with how the truth values of simple sentences determine the truth values of compound sentences. So that's one of the first things that we're going to be able to do in this course. So we're going to stick with formulas rather than sentences from now on. So for the 5 formulas above, in this course, we're going to figure out, like, say, if P is true, Q is false, R is false, and S is true, we can always know for certain what the truth value of that compound formula is. So this is the first task of this course. Like, say we have the second compound formula up there. That second formula, not P or P. If P happens to be true, right? If P is true, then not P, that's going to be false. But of course, P itself is true. So if we have a false statement or a true statement, well, then that option given to us, the whole well-formed formula there, is going to be true. Okay, and we'll talk about that more on the next slide, about exactly how to determine if something is true or false. So it's kind of confusing here, but here's the main point. If there are letters and connectives and they all are put in a nice way, then it's called a well-formed formula. And in this course, we're going to be concerned mainly with whether those particular simple sentences, those particular variables, P, Q, R, S, T, U, V, whatever variables are we're working with, we care only about whether they're true or false, right? And in a sense, that's going to stand for all situations, right? So if we have P, Q, R, whatever, um, we can we're going to make some assumptions about whether they're true or false, and then we're going to deduce more facts. So in this course, these letters are often going to act as variables, not as specific simple sentences. However, if we have specific instances, we can always use letters to represent those situations. But in this course, we're often just going to work with the letters themselves. So a few notes here. The and symbol, other than and, the technical name for it is called a conjunction. Now, if you've ever had Spanish, the word con, that means with, so that can maybe help you understand why this is called what it is. But conjunction is always going to refer to and. And the or symbol, other than being called or, it's also called the disjunction. And finally, the not symbol is called the negation, or the logical negation. The and is sometimes called the logical conjunction. The or is sometimes referred to as the logical disjunction. And the the not symbol is often called the logical negation. Now, whenever we see well-formed formulas, usually in our heads we're just gonna read it as and, right? Like P and Q, P or Q, not P and not Q, things like that. So we'll use the words in quotation marks when we read it, but it's just good to know that they have more technical names as well. Okay, so one more point here. If a letter is just sitting there by itself, sometimes we might refer to it as an atomic formula. And notice the word there, atom. An atomic formula, that's going to be just a formula that's the most simple kind of formula you can possibly create. And that's just a single letter by itself, right? A well-formed formula, it doesn't have to be this complicated combination of letters and symbols and connectives. It can just be a single letter, just that represents some simple sentence. And a really great analogy here is the fact that the primes are kind of an atom for integers. So a prime number is kind of like an atom, and a composite number is kind of like putting atoms together, like putting primes together through multiplication to make a bigger number. Kind of the same thing here. An atomic formula you should just think of as the simplest kind of formula, just a letter sitting there by itself. So another point about all this is that obviously simple sentences or just variables that are by themselves, like just P, Q, and R, they are either true or false. Now, compound sentences, they are also either true or false, not both and not neither. And the point is that so any well-formed formula that contains any number of variables, any number of connectives, that well-formed formula, no matter how complicated it is either true or false. And it being true or false depends entirely on whether the letters involved are true or false. So if we have a formula like bracket P or Q bracket and R, that formula, whether it's true or false, it depends on whether P is true or false, Q is true or false, and R is true or false, right? So maybe if we have some complicated formula, maybe it happens to be true if P is true, Q is true, and R is false. Or maybe it's also true if P is false, but Q and R are true. And maybe it's false every other time, every other possibility. But we are going to figure out exactly when complicated formulas are true or false, depending on whether the constituent parts or the letters themselves are true or false. So it doesn't matter really in this course what the letters represent, because really they could represent any number of things, right? If we have a formula and we say that P is true, Q is false, and R is false, then really P could represent any true simple sentence at all. And Q and R, those two letters could represent any false simple sentence, right? So when we talk about formulas here, we're really talking about all possibilities here, right? We don't care about particular examples or particular instances, right? When we have formulas here, we just care about whether the letters themselves are true or false. Because really they could represent so many different sentences, right? But we don't care about what they could represent because there's just so many possibilities, right? We're just going to deal here with, first of all, the letters. They're either true or false. Therefore, the larger compound formula is either true or false. So here I'm going to give a few more comments about negation in particular. So remember the tilde symbol or the little squiggle? That represents logical negation, right? We read it as not. It's also called the not symbol. Okay, so I have a statement. I'm going to call it statement number 1. Fire is hot. Now that's a simple sentence, of course, because there's no connecting words used there. It's very simple. Fire is hot. Now we could choose to let the variable P represent that sentence, that fire is hot. Now this you don't actually have to remember, but in mathematics, if you want to define a variable, oftentimes they'll use a colon and then an equal sign. And that literally means is defined to be. So if you want to define a variable like a mathematician would, you would just write the letter, right, like P or Q or R, and then you'd write the is defined to be symbol. And then you would write what it is or what you want to define it to mean. So in this case, we're going to let the letter P be defined to be the sentence, fire is hot. Now, in the English language, you could disagree with this assertion in many different ways. You could say fire is not hot, fire isn't hot, fire is never hot, or you could say it's not the case that fire is hot. Now, each of those English sentences is a denial or negation of sentence 1. Now, since sentence 1 is true, if you deny a true statement, it must be false, right? So, indeed, this is the essential idea of denial. The denial of a true sentence is a false sentence. And also, the denial of a false sentence is a true sentence. And of course, we've already said we're going to use the tilde to negate a formula, right? So if the letter P is a true sentence, then not P or tilde P is a false sentence. So fire is hot, represented by the atomic formula P. Now remember, an atomic formula is just a formula of a single letter. If the statement fire is hot is represented by P, then if you were to say fire is not hot, fire isn't hot, fire is never hot, or it's not the case that fire is hot, all of those are different ways in the English language of saying the same thing that we can just represent by not P. Okay? So this symbolic logic here, oftentimes we use these symbols because they really nicely represent many different ways of saying the same thing. So if you know what P is supposed to represent, and then you see the symbol not P, it's just the negation of P, right? It's pretty clear what the meaning is. You can think about it in English in your mind in any way that you choose, right? As long as it's a negation, right? If P means fire is hot, and then you see the symbol not P, well, it just means that fire isn't hot, or it could mean it's not the case that fire is hot, right? They're all the same thing being represented by the same formula. Now, here's one point. If you use the negation symbol twice, like if you say tilde, tilde, P, well, the first tilde is negating not P, right? So if P is true, then not P is false, and then not P would be true, because you're negating the negation of P, right? So it's important to understand that if there's an even number of tildes, then they all cancel out basically. And if there's an odd number of tildes, I mean, both of those situations are kind of ridiculous, but it is important to know the negation always takes the truth value of what you're negating and just flips it. So oftentimes you'll have a tilde in front of a complicated formula. Whatever the truth value of the complicated formula is, the tilde just gives you the opposite truth value. Now, this is the last slide that has lots of words on it, okay? We're going to move into a lot more just pure symbols, right? We're going to be moving from less of English examples, like in the English language, and we're going to talk about just the symbols themselves. So we're about to introduce the concept of a truth table. Now, a truth table, what this is it's going to be something we can use to determine any possible formula we can think of, any well-formed formula. We're going to be able to figure out whether it's true or false, depending on whether P and Q are true or false. So this first table is called the truth table for conjunction. Now basically what this is that final column there, P and Q, that's a formula. P and Q, that's a formula. That column there tells you what the truth value of P and Q is based off of whether P is true and Q is true or not. So the first row of that truth table says that if P is true and Q is true, well then P and Q is true. Okay? Now this makes sense because if you take two true statements and then you stick an and between them, that result, that compound sentence, is going to be true as well, right? If you say the capital of Idaho is Boise and the earth is round, right? That whole sentence is true because those two particular parts were true. Both parts were true. Now the thing about conjunction though is that if either part is false, then the conjunction is false. Right? So if P is true but Q is false, then P and Q is going to be false, right? Because P and Q is basically saying P and Q, right? Well, it's false if one of them is false, right? And of course, also if P is false and Q is false, then P and Q is false. So what the truth table does is it gives all possibilities for if P is true or false and if Q is true or false. All possibilities are captured by the truth table, right? So a truth table takes all possible ways of a letter being true or false, and then it tells you what the result of what the truth value of the entire formula is based off the truth values of the letters in that formula. So for the logical disjunction, or the or, right, if you look at the truth table, you'll see that if either one of P and Q, if either one of those letters is true, then the or is true, right? Because an or is giving you like an option, right? P or Q means either P is true or Q is true. So the first three rows are all true for P or Q because at least one of P or Q is true. Now in mathematics, if P is true and Q is true, we're still going to say that P or Q is true, even though that it kind of feels a little weird to say 2 plus 2 equals 4 or 1 plus 3 equals 4. I mean, it's not like we have an option, right? Like either one of them's true and the other one's not, or the last one is true and the first one's not. Actually, if both of them are true, then the or is true, right? That's fine. The only case that is false is if both P and Q are false, right? So if P is false and Q is false, then the statement P or Q is false. And then finally, we have the truth table for negation. Fairly simple. If P is true, then not P is false. And if P is false, then not P is true. So we are going to learn how to make truth tables for much more complicated formulas. And we always start out by listing all of the possible truth values of the letters involved. So as you can see, there's sort of a systematic way of putting truth values in the columns P and Q. Notice, for example, in the conjunction truth table, under the P column, it goes true, true, false, false. That's because for when P is true, we need one row for when Q is true, but we need another row for when P is true but Q is false. And then likewise, there's two false rows for P because we need two cases of P being false because Q could be true or false. So notice the way that we write down true and false in each of the columns, because when we have more complicated formulas, we're going to use the same pattern. So whenever there are two letters involved, the first letter is always going to go true, true, false, false, and then the second letter is always going to go true, false, true, false. And then whatever the next formula is, we're just going to write down whether it's true or false based off of whether P and Q are true or false. Okay, so let's now talk about a really useful tool that we can use in order to actually construct these truth tables. Alright, so let's say that we want to figure out what the truth table is for each of these formulas. We know what the truth tables are for P and Q, P or Q, and not P. Now, obviously, since we know the truth table for P and Q, it's going to be the same truth table as for R and S, for example, right? The actual letter doesn't matter. But the fact is, we have the truth table for P and Q. So we should be able to figure out the truth table for P and not Q. Since in this first example we have P and not Q, well, that part at least, we can know if it's true or false based off of whether P is true or false and Q is true or false. So let's just, for sake of simplicity, let's assume that P and Q and R and S are all false, right? We're going to assume that they're all false, all four of those letters. So since P is false and Q is false, not Q is going to be true. And so P and not Q, well, that's a false thing and a true thing. Now, combined, that P and not Q is false because P is false, right? If we have an and, both parts need to be true in order for the whole thing to be true. So since not Q is true, that's great, but P is false. So that whole section there, the P and not Q, that part is false. Now, this part on the right, not bracket R or S, well, R is false and S is false. And if you remember from the truth table for OR, at least one of them needs to be true in order for the OR to be true. So since both R and S are false, the OR is false. But the not, there's a logical negation symbol there. So that means that the part on the right there, the not bracket R or S, that whole thing is true because R or S was false, but not R or S is true. So P and not Q was false, and not bracket R or S was true. Can a false statement and a true statement, can that conjunction be true? No, because the first part of the conjunction, the P and not Q, was false. So there's 5 bullet points here. That first bullet point, that formula is false if we assume that P, Q, R, and S are all false. So if we were to make a truth table for that first formula, the very last row where P, Q, R, and S are all assumed to be false, then the final formula there would have to be false for that row. Now, for 4 letters, there's a lot of possible combinations of true and false that we could assume. We've just figured out one particular case where all of them are false, but actually, because each of the letters has 2 possibilities, either being true or false, there's 16 total options here. So our truth table would have 16 rows. Now that's quite a large number of possibilities. We're gonna look at decomposition trees in order to figure out, in order to kind of make this simpler for ourselves. So a decomposition tree, it's going to break up a complicated formula into simpler parts. So the first thing that we need to think about when we're going to create a decomposition tree is we're going to look at the formula and think about, well, how could we break this up? Like, what is the most external connective, right? Like, if we were to make this formula, what connective was added last? It looks like it's that and right there in the middle, right? Because there's 2 formulas in brackets on its left and right side. So that and in the middle is the last connective. So if we're going to decompose this formula, we're going to decompose it into the 2 parts, P and not Q, and then the other part is going to be not bracket R or S. And then when we look at P and not Q, that part right there we can decompose into 2 parts, just P by itself and not Q by itself. And over on the right hand side, the not bracket R or S, well, in our decomposition tree, we can decompose that. We can just take off the negation symbol, basically. And that's what we're going to do, right? We're going to take off the negation symbol, and we're just going to think about R or S. And then at that point, R or S, we can decompose into its two parts, R, just R, and then just S on the right. So we'll have an example on the next slide. We're going to have an example of a decomposition tree of a formula. All right, so here is a decomposition tree. So as you can see, the original formula is on top, and the formula has been broken up into two pieces such that those two pieces only need one connective in order to make the original formula. So as you can see, there's only one way to break up that formula on the top into two pieces so that we only need one connective to insert in between those two formulas to make the formula on top. So in a decomposition tree, at each step, we're going to remove one connective at a time. And we're going to continue to remove connectives until we're left with just all of the variables left. So as you can see on the left, the P and not Q, we can break that up into the P and the not Q because all we need is to insert an and symbol in between the P and the not Q to get the P and not Q. So we removed the and. And then, as you can see, whenever a formula is being negated, the next step in the decomposition tree is just simply to remove the negation. And as you can see, the P was already at just the variable on the second level lowest to the bottom, and so we just kept it as P on the bottom level just so that all of the letters by themselves appeared without any connectives at the very bottom of the tree. So it turns out that decomposition trees can help us construct truth tables for really complicated formulas. So whenever we have a complicated formula and we want to know what its truth table is, and again, remember, a truth table, it tells us what the truth value of that complicated formula is, depending on what the truth values of the atomic formulas are. And remember, the atomic formulas are just the letters themselves. They're formulas that are only one item. So once we have our decomposition tree, we're going to construct the truth table by first listing each of the variables in alphabetical order. So basically just the bottom row of a decomposition tree, those are going to be our first few columns. So in this formula, since there's 4 letters, the first 4 columns of our truth table will just be P, Q, R, and S. And then each time we're going to go up the level of the decomposition tree, and we're going to list those formulas as columns. So obviously we already have P as a column, so we don't need to do that again. But the 5th column in this truth table will be not Q, and the 6th column would be R or S. Now technically, you can do not Q, an R or S. You can do those in either order, as long as you do everything in the second bottom row, and before moving on to the third bottommost row. So our truth table is going to have the P column, the Q column, the R column, and then the S column. And then the 5th and 6th columns can be not Q and R or S in either order. And then the 7th and 8th columns, those are going to have to be P and not Q and not bracket R or S. So those are the 7th and 8th columns. And then the 9th column is just going to be the final compound formula that we started with. So hopefully it's fairly clear how to create a decomposition tree based off this example. In your homework today, you'll have a few examples of formulas where you'll have to construct the decomposition tree, and then also you'll have to draw the truth table after that. And we'll have an example of how to make a truth table of a complicated formula very soon. But for now, just remember that we remove one connective at a time from the formula, breaking it into smaller pieces, and whenever there is a negation, logical negation, we just we take one step to remove that logical negation. Okay? So, and then in our truth table, we're always going to list the atomic formulas, or in other words, the variables, in alphabetical order, and those will always be the first few columns of our truth table. And the next columns of our truth table, we're just going to go up a step in that decomposition tree to where we have the P, the not Q, and the R or S. Now P was already a column, right? So we don't need to make a column for that again, but we're going to make a column for not Q, which, notice, should be pretty easy, because if we have a column for Q, the column for Q is going to have some trues and falses, right, as possibilities. In the not Q column, we're just going to do the opposite truth value of whatever the Q column was. And notice in the R or S column, we're just going to look at the column of R and the column of S to determine what the truth value should be in the R or S column, right? The only way that R or S can be false is if R is false and S is also false at the same time. So let's go ahead and look at a truth table. So here's an example. My drawing of the decomposition tree is a little bit clunky just because I didn't use a very good software to make it, but hopefully it's pretty clear what it's supposed to be. So here's an example. So we're going to construct the decomposition tree and the truth table for the following formula: not bracket P and not Q bracket. So then the decomposition tree, we're going to take away one connective at a time, and we're going to take away the negation first. Okay, so whenever we have a negation, whenever our formula is the negation of another formula, the next step in the decomposition tree is always just to remove the negation. Okay, then we're left with P and not Q, and then we're going to remove the logical conjunction, right, the and. So then we're just going to have P on one branch and not Q on the other branch. And then finally, we're just going to write P again, just so that it's clear what the atomic formulas are, or what the variables are at the bottom. And then we're going to take away that negation on the Q, and we're just left with Q. So hopefully the procedure for creating a decomposition tree is fairly clear by now. And hopefully this example, you'll see why the decomposition tree is super useful in constructing truth tables. So, in this truth table, we have two atomic formulas, we have two variables involved, so we're going to list them in alphabetical order. The P goes first, and then the Q. Now, depending on how many variables are in the formula, that's going to determine how many rows you're going to need altogether. Now, since there's only two variables, there's only 4 possibilities of truth and falsity for P and Q. Only 4 possible combinations of true and false, right? They could both be true. One of them could be true and the other one could be false. Or, the other way around, one of them's false and the other one's true, or both of the variables are false. And that covers all the possibilities. So you might want to think to yourself, well, if there's 3 variables, how many possibilities are there going to be? Well, you can list them out and then count. There should be 8. So if there's 3 variables, there's going to be 8 rows in your truth table, right? And actually, there's a quick computation that you can see how many rows you're going to need. All you have to do is you have to take how many variables you have, and you're going to raise 2 to that power. So 2 to the second power gives us how many rows we need for 2 variables, and 2 to the third power, or 8, will tell us how many rows we need for 3 variables. And that's because there's always 2 possibilities for each variable, so we're just going to multiply 2 as many times as there are variables to get all the possibilities. So that's how we compute how many rows are going to be in our truth table. Of course, we're not counting the top row that just labels the columns, right, to tell us what formula we're finding truth values for. In listing the truth value possibilities for P and Q, you always should do it in the following way. So if there's two variables, for the first variable, you're going to do true, true, false, false, and then you're going to go true, false for the second variable. And if there's three variables, you'll do true, 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 false, 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 true, true, false, false, true, true, false, false for the second variable, and then true, false, true, false, true, false, true, false for the third variable. And then notice in this truth table, in the not Q column, we're just doing the opposite truth value of whatever the Q was. So the Q column goes true, false, true, false. So the not Q column is just going to go false, true, false, true. Now recall that a logical conjunction, or an and formula is only true if both of the parts of it are true. Okay? So if we look at the P and not Q column, we need P to be true, and we also need not Q to be true in order for P and not Q to be true. So notice that P and not Q is only true in one case, and if we look down, both P and not Q, both of those by themselves are true in that case. And in every other case, P and not Q is false. And then this makes the final column super easy because this is just a negation of the column before it. It's not bracket P and not Q, which is just going to have the opposite truth value of whatever P and not Q had as a truth value for that row. So notice P and not Q has a column of false, true, false, false. So the not P and not Q column is just going to be the opposite truth value. So we're just going to have true, false, true, true. So notice how we're kind of building up to our original formula, right? We're starting with all the variables that are involved, and then we're slowly adding the connectives until we finally have the last column of our truth table is the formula that we wanted all along. So hopefully you can see how the decomposition tree helps us construct that truth table. Right, so remember when we're constructing truth tables for a particular formula, some complicated compound formula, the first thing we do is from left to right by columns, the atomic formula should always come first. Right, so we want the simplest possible parts of the formula to come first. And then we're going to list the atomic formulas in their alphabetical order. So we're just making sure the letters come in alphabetical order. And as a general heuristic for the ordering of the columns, we're going to go from the bottom of the decomposition tree, right, the very bottom, which was just the variables by themselves, right? Then we're going to go to the next lowest row of the decomposition tree, and we're going to include those formulas as columns in our truth table. And then we're going to go one step higher to the next the third lowest row in the decomposition tree, and we're going to include those formulas in our truth table. And then we're going to keep going up the decomposition tree until we finally get our original formula, which is what we cared about all along, of figuring out what the truth values of the original formula was. And then as a reminder, if you're wondering how many rows do you need in your truth table, just take the number 2 and raise it to the power of however many variables you have in your formula. So if there's a formula that just involves P, like maybe the formula is not bracket P and not P, or something like that, even though it's a complicated formula, there's only one variable, P, involved. So you're just going to have 2 to the first power rows. So just 2 rows, which makes sense because you're going to need a row for the case when P is true, and you're going to need a row for the case when P is false. And if there's 2 variables in your formula, like for example, not P and Q, that's a formula that has 2 variables. You're gonna use 2 to the second power, or 4. You're gonna use 4 rows in your truth table. And then if you have 3 variables, you're gonna use 2 cubed rows, or 8 rows. And if you have 4 variables, you're going to use 2 to the 4th power rows, or 16 rows. Notice that each time you add in a variable, like that variable can either be true or false. So if you add another variable, you're going to need all the possibilities that you already had with the variables that you already had, but you're going to need 2 cases. You're going to need 2 copies of all of those possibilities because your new variable could be true or false. So we always are going to multiply by 2 whenever we add a variable. We're going to multiply by 2, and that's how many rows we're going to need. And in general, we're just going to start with using the letter P. And this is just generally what we're going to do in this class. Just use the letter P as the first letter if it's not used up already, and then just go to Q, and then go to R, and then go to S, and then go to T. You probably won't use S and T too much in this class, but you will need it on occasion. And also, don't worry about so many variables and creating super huge truth tables. After a couple classes, we're not going to require you to draw truth tables anymore. And that's just because we're going to be doing logic without truth tables. And we always have truth tables if we need them, but really the logic will take care of whatever we would need from truth tables. So in particular, by the end of this week, once we get to start learning about demonstrations and how to use them, how to create them, by then we won't need truth tables anymore. Alright, so hopefully if I give you a formula, you should be able to construct the truth table for it, and construct the decomposition tree for it. Hopefully doing the decomposition tree first, then it will make it easier to see how to make the truth table. And of course, if you have any questions about any of this content before we meet on Wednesday, feel free to email me with any questions that you have, and I'll get back to you as soon as possible. And also make sure to bring your homework with you on Wednesday from the first 2 days. So the first 2 days homework, I'll just have you bring it in on Wednesday, and I'll grade it, of course, and we'll also take 2 quizzes on Wednesday. And they won't be super hard quizzes. They'll just be about decomposition trees and truth tables. And it won't be super hard, but it'll just be to see how you're doing so far with the content. And I know that video is not always the best way to learn for some people. So we'll just use Wednesday as a day to make sure everyone's on track, and then we'll continue on with the content from there. Okay, so now I have somewhat of a challenging question for you, but I want you to know that the answer to these questions are actually very, very answerable, and logic can answer these questions. So take a look at these formulas. Now, we already did some things with these formulas earlier. I think these were the formulas that I wrote down on a previous slide. But take a look at these formulas and think about these questions. The first question I have for you is, if I told you that the first formula was true, so if I told you that that entire formula has a truth value of true, could you figure out what the truth values of P, Q, R, and S are? Now, it might be the case that multiple possibilities could be for P, Q, R, and S of their truth values, but they also could be forced. And what I mean by that is, if we take a look at this first formula here, if we know that that formula is true, then because the last connective in there is an and, well, the formulas on both sides of the and have to be true as well. So that means that P and not Q has to be true, and also not bracket R or S has to be true. So if that's the case, so P and not Q is true, but P and not Q, that's a logical conjunction. So if P and not Q has to be true, well, then P has to be true and not Q has to be true. So that means that Q has to be false. So we know that P is true, Q is false, and okay, but we also have that not bracket R or S is true. So that means that if we take that same formula without the negation, if we just have R or S, well, that has to be false. But the only way for a logical disjunction to be false is if both parts of it are false. So we have R is false and S is false. Well, now we know what the truth values of P, Q, R, and S are, right? So if the first formula, the whole thing, if the first formula has a truth value of true, in this case, it's definitely possible to know exactly what the truth values of P, Q, R, and S are. Okay, so for the second question, can you see why the second formula is always true no matter what the truth value of P is? Okay, first of all, a note. If that formula is always true, no matter what the truth value of P is, that means that the last column of the truth table is all T's, right? That means that no matter what the possibilities of the truth value of P is, at the end, the final formula is always true. Well, if we take a look at this formula, not P, well, that's the same thing as just not P, right? So is it always true that no matter what P is, if P is true, well then we have P being true on the right, and we have either not P or P, well, obviously that's going to be true. And hopefully by now you kind of see that what we're doing right here is kind of like a form of logical deduction, right? We're kind of deducing what the truth values of these letters have to be based off of information we already have, right? And what we're going to do in this class is we're going to learn a very clear and logical process so that we don't have to guess how to figure things out. We can actually figure them out through a very, very nice method. Okay, the third question. If I told you that the last formula is false, and also that Q is false, what can you tell me about P and R? You can pause the video to try this problem, right? You know that the entire formula is false, and also you know that Q is false. Can you deduce what the truth value of P is and what the truth value of R is? So the answer is, because this big formula here at the bottom, P and not Q, or bracket not P and R, this is a logical disjunction of two smaller formulas, okay? And if a logical disjunction is false, that means that both parts have to be false. So P and not Q is false. Okay, well that means that P has to be false. Well, actually, no, never mind. If P and not Q is false, that means that at least one of them is false. But we know that Q is false, right? The problem tells us. So that means that not Q is true. Well, P and not Q is supposed to be false, so P must be the false one. So P is false, Q is false because they tell us. Now if P is false, if you look over there on the right, not P and R, now remember, because the entire formula is false and it's a logical disjunction, not P and R has to be false. But remember, we actually know that P is false, so then not P is true, but then that forces R to be false in order for not P and R to be false. Now, if it was hard to follow that, that's okay, because throughout this class we're going to learn a nicer process to arrive at that conclusion. Okay, so we're about to get to our 2-hand-in assignment for today and our 4-class assignment for today. Now, I will include a PDF link in the description of this video, so go ahead and open that link if you can, or after the video, I guess, whenever you want. The homework is going to be on that link, and yeah, the instructions are on there, and the problems are on there, and try to get that in by Wednesday. There will also be a homework assignment tomorrow. At the end of the video, I'll give a link in the description of the homework tomorrow, and just make sure to get both of those assignments done by Wednesday. But here, I just have an example of the 4 class problems and the 2 hand-in problems. So if you look at the document, you'll see that the 4 class assignment, it'll give you a sentence, right? And the sentence here is, it's not true that Joy pulled the fire alarm and didn't exit the building. And what we're going to need to do for that sentence is you're going to need to define atomic formulas, or remember, define variables for the sentence. So you're going to identify what the simple sentences are in that sentence, and then you're going to let the variables be those simple sentences. So in the sentence, it's not true that Joy pulled the fire alarm and didn't exit the building. You're just going to let P be Joy pulled the fire alarm, and you're going to let Q be Joy exited the building. And then you're going to find out what the formula is for that. You're just going to interpret the sentence, and the formula is not bracket P and not Q. So that's going to be your 4 class assignment today. You're going to be given a sentence, and you're going to define variables for them, and you're going to say what those variables represent in the sentence, and then you're going to find an actual formula for it. Now for the 2 hand-in assignment, you're going to be given a formula, and you're going to be told to draw the decomposition tree for that formula, and you're going to be told to draw the truth table for that formula. So here's an example. Say we were given the formula not P or Q. Right here we have an example. We have the decomposition tree drawn, and then we have the truth table drawn. So for the decomposition tree, I would recommend doing that first. The connective that you're going to take away is the or, and you're going to be left with not P on one side and Q on the other side. And then there's one last step to finish off the decomposition tree. You're going to take away the negation connective for the P, so you're just left with P, and then you're just going to write Q again so that it's in line with the P. And then for the truth table, right, there's 2 variables involved, so there's going to be 4 columns. And whenever there's 2 variables involved, the first 2 columns are always going to be just all possible possibilities. And I want you to write them as true, true, false, false, true, false, true, false. Okay, and then for this truth table, the 3rd column is going to be not P, because that's in the 2nd most bottom row of the decomposition tree. Q is we already have a column for Q, so we just need to make one for not P. And to make the not P column, we're just going to look at the P column, and whatever the truth values were in that column, we'll just do the opposite truth value in the not P column. So since the P column was true, true, false, false, the not P column is just going to be false, false, true, true, right? And then finally, we have the final column of the truth table, and that's just going to be our original formula, not P or Q. So to figure out what the column is going to look like for not P or Q, because it's a logical disjunction, right? It's an or. We're going to look at the not P column and the Q column, and if at least one of those is true, then the logical disjunction is going to be true. And the only case when not P or Q is going to be false is if both Q is false and not P is false. And you can see in the 2nd row that's happening. But in all other cases, not P or Q is true because at least one of Q and not P is true. Okay. So hopefully today's lesson was fairly clear. Of course, email me if you have any lingering questions. And yeah, the PDF to the homework assignment should be in the description. And you can go ahead and get on a separate sheet of paper. You can just write your homework on that and then turn it in to me on Wednesday. And I will get the 2nd video, Tuesday's lesson. I should be posting that sometime on Monday probably. so the day before. Until then, feel free to go through this video again. If you need to go through it again, feel free to practice or ask any questions. And yeah, good luck with the homework, and I'll see you in the next video.